Hi, hope everyone's well today. It's time to start the new outcome of Engineering Maths 5, and that is partial derivatives. You will see on Microsoft Teams there is a booklet that looks like this. Now the front cover might be slightly different because it might be a slightly older book. It doesn't matter, that it's the exact same stuff. Now, unlike second order differential equations, the stuff at the top we've just been doing, this book is printed properly. So we can use the question sheets in it, we can use the examples in it, we can use the notes that are given in it. But as usual, I'll be doing full lectures to supplement the notes. Now, if you look at the picture on the front of this booklet, this is a surface. It's a three-dimensional surface. And as you can see on that surface, there are maximums here and here, like hills. There are minimums going down here and going down here. And then in between the two maximums is a thing here called a saddle. So what partial derivatives allow us to do is deal with three-dimensional planes or three-dimensional surfaces. It allows us to find maximums and minimums. And in engineering, we know 3D surfaces are really important. You'll see lots of buildings are built using this form of mathematics because we don't really deal with 2D that often. We far more often deal with 3 dimensions. Right, so let's get on with this. So, partial differentiation. So, partial differentiation allows us to find maximum, minimum, and saddle points on three-dimensional surfaces. And I might use the phrase planes. Right? I don't mean like aeroplanes, I mean like this sheet of paper in 3D is a plane. Right? We're not just dealing with lines now, we're dealing with planes. Now, normal differentiation, we write is just dy by dx. Normal differentiation, just like that. Now, partial differentiation or partial derivatives, we use a curly d like that. That means partial dy by dx or partial differentiation. Right. Now, as you know, we're going to be dealing with x, y and z coordinates because we're going to be dealing with 3 dimensions. Right? Dealing with functions involving x, y, and z this time. Okay, so partial differentiation allows us to find maximum, minimum, and saddle points on three-dimensional planes or surfaces. Now, normal differentiation is just dy by dx. Partial differentiation is curly dy by dx. And because we're dealing with three-dimensional surfaces, we're going to be dealing with x, y, and z. Right. So, example 1. And all we're going to do in the first bit is just get used to the calculations. Right, that's all I'm looking for, is to get used to, is the calculations. So 1, just done that. So z equals x squared plus 4y plus 3. Right, now the question is going to ask you to find two derivatives, because you can differentiate x or you could differentiate y, right? Now what this means here is differentiate x's and treat y as a constant. Okay, so you differentiate your x's and you treat y as if it's a constant term if you're looking to partially differentiate z with respect to x. The x's are getting differentiated, the y's are getting treated as if they're a 2 or a 4 or something like that. Right, here, this is just the opposite. We're going to differentiate the y's and treat x's as a constant. I know people find it quite easy to always think about the second or the letter you're taking as a constant, thinking of it as what would happen if it was a 2. That's what I tend to do when I'm doing it. Right. So let's look at an answer. So dz, partial dz by dx. Right, so if I differentiate x squared, that just gives me 2x. Now, remember, y is just a number, right? So that just becomes 0. That's just a number, so when I differentiate it, it becomes 0. So that just means that dz, partial dz by dx is just 2x. Okay, so let's look at, I'll just split the pages down the middle here, make it easier for me to do both. Right, so let's look at partial dz by dy. Okay, so remember, if it's an x by itself in some way, it just becomes 0, because it's just a number, and we know if we differentiate a number, it becomes 0. So that's just going to be 0. If I differentiate 4y, I just get 4. And again, if I differentiate a number, I get 0. So partial dz by dy is 4. And those are my two derivatives. Let's look at a second example. Right. Right. Example number 2. So again, z is 4x squared plus 7xy plus y cubed, and I want to find dz by dx and partial dz by dy. Right, so let's have a look at our answer. So, again, let's start first with dz by dx. Right, so, differentiate x is normal, right, because it's the x that I'm differentiating with respect to. So, if I differentiate 4x squared, that just becomes 8x. Right? Now, if I differentiate the x, it just becomes 1. And remember, these are both constants. So that's just going to be 7y. That's just a y by itself, y cubed. So that just becomes 0. So dz by dx is 8x plus 7y. Okay? So let's look at partial dz by dy. Okay, so we're differentiating with respect to y. So this bit, you just get x's in it, so that's just going to become 0. This is get x's and y's in it. Differentiate the y, I get 1, but remember, that's just a constant, that just becomes 7x. If I differentiate y cubed, it gives me 3y squared. So that's just 7x plus 3y squared. Like that. Okay. Example. So now all other differentiation rules apply in partial differentiation. Okay, so that means we've got chain rule, product rule, quotient rule, parametric. Parametric differentiation we met back in Engineering Maths 3. Right, so obviously we've done 2 basic examples. So next thing we're going to do is look at stuff involving the chain rule, product rule, quotient rule, and eventually we'll get to parametric differentiation. So, first example 3, and this says z equals 3x squared plus 4xy to the power of 6. And we're going to find partial dz by dx and partial dz by dy. Now you may also see that written as f open bracket x comma y close bracket, right, just saying a function of x and y, but I prefer to deal with it as z because the use of this is normally to deal with 3D space. Right, so I see my bracket with a power on it and I know that is the chain rule. So I'm just going to write down the question to start off with because it gives me more room to show you the working. Right. So z is 3x squared plus 4xy to the power of 6. Right, so the rule with the chain rule is you differentiate the outside of the bracket, leaving the stuff inside the bracket the way it is. Just like that. And you multiply it by what you get if you differentiate the inside of the bracket. Okay, so if I differentiate this with respect to x, I get 6x. And if I differentiate this with respect to x, well, that x just becomes 1, that just becomes 4y. And that's as simple as it goes. Now, tends to be you always write the bracket with the lower power on it first, but makes no difference. Right, now I need to work out partial dz by dy. I'll just draw a line here saying that's the first bit worked out. I'm going to work out the second bit. Right, so again I've got y in the bracket, so I know it's the chain rule. So same thing again, you imagine the inside of the bracket is the big y, so that's going to be 6 bracket to the power of 5, and the bracket stays the same. Multiply by what you get if you differentiate the inside of your bracket. Now if you differentiate the inside of that bracket with respect to y, that just becomes 0. If I differentiate that with respect to y, well that just becomes 1. And those are constants, so that just becomes 4x. Okay, so that's the final answer to that question there. Now, what I would ask you to have a look at is go to the partial differentiations, partial derivatives booklet, this one here, and go to page number 9. Okay, so this is page number 9 with the questions on it. It might be slightly different in the book I've put up in Teams, right? And I want you to try questions 2, 3, 4, then 1. Okay, so we have to do 2, 3, 4, and then number 1. Now, as usual, the answers to those questions are at the back of the book. So this one here will just be normal. This one here is chain rule. This one here again is chain rule because of the bracket. And that one there is also chain rule. Now, see here where you've got fxy, you can just swap that for z if you want, right? And then it makes it more like the examples that I have done.